Guys, how's it going? This is Mike coming back at you with another video on discrete mathematics. In the previous video, we introduced statements with multiple quantifiers to them. We saw what these things look like, and we went through what does the negative of these things look like. In this video, we're going to go through a few samples here. We're going to see how we show that these kinds of statements are true and or false. So first one here, I have one set D, which is -5, -3, -2, and -1. And then I have the set E that contains the numbers 2, 4, 5, and 8. And I'm going to look at the following quantified statement. For all x in D, there exists y in E such that x plus y is greater than 0. This is the first of the two main multiple quantified statements that we talked about in the previous video. We said that for this particular type of statement, you let somebody else, and I say that in quotes, you let somebody else pick a guy in the set D. Based on their choice, you pick a guy in E that will try to make the predicate true. And if you can do that, if the other person, in quotes, can take every element of D, and based on that choice, you can pick an element from E that will make the given predicate true, then your statement with multiple quantifiers is true. So that's what we're going to show for this statement here. We're going to show that this statement is true, and we're going to show so by the method of exhaustion. So I'm going to simultaneously pretend I'm somebody else, and I'm going to be myself. We'll go through every case where we'll see that for no matter what x value I choose from set D, I can find a value from set E, and those two values, when I plug them into my predicate, will make it true. So first case, if x is equal to -5. So the guy in set D was chosen for me by somebody else. I now choose a guy in E. So I'm going to choose y is equal to 8. In that case, when I have x equals -5 and y equals 8, x plus y is 3, and that is greater than 0. That is positive, obviously. So that's one case that I had to show. I will now let x equal my -3, and I'm going to choose another y value. I chose 4 in this case. And you can see, obviously, that x plus y is going to equal 1, and that is positive. Now, you don't necessarily have to choose a different y value. You could have chosen the same one, but I just chose to not use the same y value for all of these 4 cases. That's just my personal choice. So we've shown it for the second case. Somebody else chose -3 for me. I then found a guy in my set E that will make this work. If somebody chose x equals -2, I can choose y is equal to 5. -2 plus 5 is 3. 3 is positive. That makes my predicate true. And last choice for x that hasn't been made yet, x is -1. I can choose y is equal to 8. I could have chosen any y value there. I could have chosen 2, 4, or 5. And no matter what, x plus y would still be positive. So this is how we show this for all, and then there is multiply quantified statement true. You go through every possible choice of x in D. Given that arbitrary, in quotes, arbitrary choice of x in D, you pick a y value in E such that those two values will make your given predicate true. different numbers in these domains D and E. D contains -1, 4, 2, and 10. E contains -3, -7, 5, and 11. And we're going to consider the following quantified statement. There exists X in D such that for all Y in E, X times Y squared is less than Y. Now, a quick note about the domains D and E up here. Notice that in the previous sample, I wrote the numbers in increasing order. Here I did not. That does not matter. Just as long as you have all of the numbers in there, that is all that counts. Also, when we write sets, we don't write numbers that show up more than once. We only write numbers once inside of our set. So for this kind of multiply quantified statement, there exists X in D such that for all Y in E, I have to pick one guy in D and then stick with that guy. I take that one guy, that one X value, and then I show that when I pair that X value up with every other Y value in my set E, those X and Y values are going to make my predicate true. So that's exactly what we're going to do for this problem. This is a true statement. The X value that I'm going to choose and show that this works is X is equal to -1. And I'll show that by choosing X is equal to -1, regardless of what Y value I choose. So regardless of what number in E that I choose, my predicate, xy squared is less than y, will be true. And again, we'll show this with each case. So if y is equal to -3, well, x is equal to -1, y is equal to -3, y squared is +9, multiplied by the -1 gives me -9. -9 is less than -3, and that was my y value. So we've shown that the predicate is true for when x is equal to -1 and y is equal to -3. Next up, x is still -1, but now y is equal to -7. In that case, x times y squared is -49. -49 is indeed less than -7, which was my y value. So again, xy squared is less than y. The other two cases, a lot more straightforward, a lot clearer to see that the predicate is true. X is -1 and y is 5. Xy squared then is -25, is obviously less than +5, which is your y value. And then when y is equal to 11, xy squared is -121, and that's obviously less than +11, which was your y value. So you see that we stuck with some x value. We fixed some x value that was in set D. And then we saw, okay, take that x value and then pick whatever y value I want. Those x and y values made the predicate true. Now, when it comes to this particular kind of statement, when it comes to figuring out whether or not this is true, you may have to do a little bit of side work, and you may have to do some trial and error to see what value in D, if the statement is true, will make or will be the guy that you want. You may have to try, okay, if I try my x value as being 2, okay, if I pick y as -3, then x times y squared is going to be 18. Oh, but that's not less than my y value of -3. Okay, so 2 doesn't work. Then move on to the next guy. Oh, and just keep going through that way. If you encounter a case that doesn't work, then that choice of x value that you tried, it cannot work. So there's one example of how we see a there exists for all multiply quantified statement is true. Here is another statement with two quantifiers in it. We're keeping the same numbers in D and E as we did for the previous problem. This one is now for all x in D, there exists y in E such that absolute value of x times y is greater than 20. So try to write the negation of this statement, and is the negation true? Otherwise, aka, is the given statement false? So I'm going to pause the video here, take some time. The negation of this statement should not be too hard, but also try to figure out, is the given statement false? In other words, is the negation, once you find it, is that true? And that may take some more time. That may take a little bit more thinking, but it's not too bad. And we'll go through, we'll sort of go through whether or not the negation is true or false and why we say that. But pause the video here, try to figure out the negation, try to figure out whether or not that negation is true, and once you think you have it, press play, and we'll see if you have the right answers. All right, so let's see if you came up with the correct negation, first of all. The negation is there exists x in D such that for all y in E, the absolute value of x times y is less than 20. It's a typo there, my apologies. That should be nothing new. That should be pretty straightforward. We saw from the previous video, when we take the negation of a statement with two quantifiers, we take the opposites of each quantifier. So the for all becomes a there is, and the there is becomes a for all. And then we negate the predicate. So now there exists x in D such that for all y in E, absolute value of x times y is less than or equal to 20. So think about that. Is that negation true? Can I pick one x value or pick one value in my set D such that if I take that x value and multiply it by any number that's in E, and I take the absolute value of that number, of that product, will it be less than or equal to 20 in every single case? And it shouldn't be too hard, and it shouldn't take too much time to figure out that, yes, that is indeed the case. The negation is true. Therefore, the given statement is false. If you choose x to be -1, once again, take x as -1, pick any y value in your set E, multiply it by that -1, and take the absolute value of it, you are going to get either +3, +7, +5, or +11, all of those being less than or equal to 20, obviously. So the negation is true, which obviously then the given statement is false. So these are just a few samples seeing how we would show that statements with multiple quantifiers are true and or not true. If you have any questions or comments, please be sure to drop them in the comment section below. Otherwise, until the next video, take it easy, folks.